Welcome to my course Electrochemical Energy Storage, and this is module number 2, definitions and measuring methods. So, this is lecture number 6, where I will talk about introduction to electromotive force, redox potential, Faraday law and Nernst law and their application. So, the concept that I want to cover in this course is the redox potential of an electrode. Then we will talk about electromotive force of an typical electrochemical cell. Then I will introduce Nernst law, followed by Faraday's law and certain illustrative examples how the Faraday's laws are used in electrochemical energy storage. So, you know that in my first week lecture, we introduced the concept of the redox, and here you can see a typical reaction. Basically, if you follow the forward arrow, then it is reduction, and follow the backward arrow, then it is oxidation of a metal. And in general, we can write that oxidant, it takes electron and eventually it get reduced, and in my last week lecture we talked about the stoichiometry should be maintained in this reaction. So, once you introduce a metal into a solution, it contains let us assume that it is having a valency N plus. So, Mn plus ions are there. So, a thermodynamic equilibrium will be established, which basically involved an oxidation reaction between metal and reduction reaction with the electroactive species, which is already existing as Mn plus in the solution. So, here I have shown the reduction part, and this typical reaction is characterized by a thermodynamic potential for this oxidation reduction, and we call this is a redox potential, and this is usually we measured in terms of volt. So, E is the terminology and it is measured in volt, and this voltage, which is oxidation reduction, this is expressed as compared to the normal hydrogen electrode, and by convention, as I have already explained, this H plus and H 2 couple, this we take as a origin, and therefore, this voltage under standard condition, that means temperature will have to be maintained at 298 Kelvin, concentration is 1 mole per liter and pressure is 1 atmosphere. So, we call this as a standard condition. So, this standard electrode potential for the reference is termed as a 0, and based on that chemists they have tabulated a table which gives the standard potential, particularly the reduction potential, and it is measured under standard condition, standard pressure, temperature and concentration of the electrolyte. So, by convention a choice is made, the negative sign with the redox potential of the reduction reaction of an electropositive material. As I have illustrated in this table, you can see that everything is basically a reduction reaction. So, the hydrogen is termed as a 0 potential, and then you have certain material which is very strongly it is reduced, and certain electropositive material which is very easy to get oxidized. So, if you combine any two dissimilar metallic conductors, they can be used to construct a galvanic cell. I already introduced the concept of a galvanic cell, and the cell potential that basically measures the energy which is available in the cell. So, this cell potential, if I define at E cell, that you can estimate from the cathode potential, that is the reduction half cell reaction, minus the anode potential, which is defined as anode half cell reaction. So, the potential of oxidation half cell reaction, as I told that it is taken negative value of the reduction half cell reaction, which is taken as positive. So, under standard condition, the cell potential is the cathode standard potential minus anode standard potential, and by standard I mean 1 molar concentration of the electrolyte and 1 atmospheric pressure, and temperature is typically 298 Kelvin. And the standard electrode potential for the reference, which is hydrogen in this case, that is taken as 0, and this is the so called reduction reaction. So, that is taken as 0. So, if you look at the component of a galvanic cell, this is electrochemical cell that uses a spontaneous reaction. So, whenever two electrode with different standard reduction potential you dip in the electrolyte. So, the reaction is spontaneous. So, it consists of two electrodes, one we call anode and another one we call cathode, that is in contact with the electrolyte, that is able to conduct ions, but not electrons. Electron will be supplied to the external load or the device. So, usually the anodes are typically zinc, cadmium or nickel. It removes electron. Sometimes they are kept in contact with a graphite current collector to take the electron out into the galvanic cell towards the load. And at cathode, the reduction reaction occurs and the electrode gives electron to the species in the electrolyte. Sometimes it is in contact with a current collector as well. And electron, as I said, it flows from anode to cathode, that is from negative to positive electrode by an external circuit and does the necessary work. So, energy is involved. And anions travel towards the anode through the electrolyte and cations travel to the cathode through the electrolyte, and driving force is the energy of the cell reaction. So, based on this I can define the Daniell cell, which already I introduced, and that basically explain the principle of the galvanic cell. So, the reaction at each electrode is a half cell reaction. So, each of this part is a half cell reaction. So, in the anode zinc is oxidized and in cathode copper ion is getting reduced to form copper metal, which is eventually deposited on the cathode plate. So, the total cell reaction, this we call a redox reaction. This is defined as zinc in solid state and copper is in the oxidized state, Cu2 plus, and zinc gets oxidized and copper eventually get reduced. So, as I told, the ion passes to the electrolyte to maintain the charge balance of the cell, and the reduced and oxidized pair of the species found in the half cell reaction, that is called as a redox couple. So, it is written as oxidized species versus reduced species. So, this is copper 2 plus slash copper, that actually defines the redox couple. And in this reaction, zinc rod corrodes and electroplating is occurring into the cathode copper cathode. So, now we are in a position to estimate the reaction free energy and equilibrium cell voltage. So, instead of measuring the equilibrium cell voltage, that is the oxidant and reductant this voltage at standard condition, directly this can actually be calculated from the reaction free energy, which is defined as del G for one formula conversion using the so called Gibbs-Helmholtz relation. And while in the first lecture we already introduced the thermodynamic concept for this course, and one can write this relation where del G is utilizable electrical energy and the reaction enthalpy is del H, and this is the theoretical available energy which is either increased or reduced depending on this T del S term. So, it is the reversible amount of heat that is consumed or released during the reaction. So, the amount of charge of the cell reaction for one formula unit conversion, this is termed as Faraday equation. So, this charge is current and time product, which is eventually the number of electrons per mole and the Faraday constant. So, with this quantity of charge, I can estimate the electric energy by multiplying both sides by oxidation, E oxidation reduction this voltage into the charge. So, that gives you the energy. So, the utilizable electrical energy is E ox reduction this voltage into the number of electrons involved, usually one formula unit of the reactant material, and F is the Faraday constant. So, this is per mole and this is actually the reaction free energy, and when the reaction proceeds, reaction takes place, then by convention this reaction free energy is taken negative. So, the energy that you can estimate from this simple relation of minus n, the product of minus n Faraday constant and this oxidation reduction potential. So, now chemical equilibrium and mass expression, this is also related. So, if I define a simple relation that a metal in solid state that is reacting with some kind of gas to form a it could be metal oxide, and this reaction free energy we take at del G reaction. So, I can define the mathematical expression of chemical potential, which already I have introduced earlier part of this lecture. So, for the product we can write this relation of the chemical potential, and it is related to its standard state and gas constant, temperature and activity of this particular species. Similarly, for the metal and for the gaseous thing also I can write the relation of the chemical potential. And then the free energy associated with this reaction is nothing but the chemical potential of the product minus the reactant. So, mu mx minus this term, and if you insert the chemical potential expression here, so you will get this relation. So, this is for the product and these are the reactant. So, this part is the standard part, and you have this RT, and this is coming from this part activity of the product and divided by activity of the metal and the partial pressure of the gaseous reactant. So, your free energy term is this is del G, this 0 is actually the superscript and Rxn is the subscript. So, this is the standard energy part and it is having this RT ln k, where k is the equilibrium constant. Now, again this free energy that is associated with this reaction is del G Rxn, and the driving force for this reaction is composed of number 1, how likely one expect the reaction to occur under standard condition, and number 2 is the reactant may or may not be in their standard state. So, the driving force which is del G Rxn for a reaction is given by this relation. This just now we have proved in earlier slides. So, this is the del G Rxn 0 is the free energy change associated with the reaction when the reactant are in their standard state. So, in the standard state, the value of K, you can see the activity of Mx, activity of M, and activity or sorry the partial pressure of the gaseous product can be taken as 1. So, in the standard state K is 1. So, ln K is 0, and that tells that del G Rxn 0 is actually the del G of the reaction. So, in equilibrium we know that this del G reaction is 0. So, if you put this value, then K is known at the equilibrium constant for this reaction. So, this K term I will replace by K equilibrium, and then this del G Rxn 0 is nothing but minus RT ln of this equilibrium coefficient. So, the equilibrium coefficient you can estimate from this relation is exponential of minus of del G Rxn 0 by RT. So, we have defined the electromotive force of an electrochemical cell for the standard condition. So, this actually is not very realistic during any chemical reactions, because the reagents that can have different condition from that standard condition whatever we have defined. So, we will introduce the Nernst law, which will enable us to express the EMF as a function of concentration of the species and of course, temperature outside the standard condition. So, again if you consider this particular relation with the potential is Eox by red. So, this will also be in the subscript. So, we have already derived that this del G Rxn is minus n Faraday constant and this potential value. So, this is the standard free enthalpy, usually it is measured in joule. N is the number of moles of electron that is exchanged during this reaction, and F is the Faraday constant. Usually the Faraday constant is estimated to be 96485 coulomb per mole, and we will calculate it later. So, this potential is the thermodynamic redox potential of the reaction where no current is flowing. So, it is under open circuit condition. So, this is measured in volt or joule per coulomb from the dimensional analysis. So, if standard condition P, T and concentration as defined earlier are fulfilled, then we can write in standard free energy is minus n F E 0, and earlier also we have derived that del G is del G 0, which is superscript, and this 0 is superscript RT ln K. So, R is the ideal gas constant, the value is known 8.314 joule per mole per Kelvin. T is taken as temperature in Kelvin and K is the equilibrium constant of the reaction. So, this equilibrium constant of the reaction from the earlier relation we can put it as activity of the reduced species and oxidized species, and this represent the activities, and we will just come back to this activity concept. So, you can combine the previous relation, we put the value for del G Rxn and this is the standard case plus RT ln K. So, now from this relation you can work out the actual value of E is E 0 minus RT by NF into ln K. So, now you can put the value of K here from this relation. So, this is E equal to E 0 RT NF ln A reduction by A oxidant. So, if you take the temperature as 298 Kelvin, that is roughly 25 degree Celsius, then this part RT by F you can estimate at 0.0257 volt, and you can also transform the natural logarithm to decimal logarithm with 10 base by this simple relation. So, alternatively you can write the relation for the electromotive force E 0 is E equal to E 0 into this will come about 0.059 by n and log of this activity. So, in general the electrochemical reaction involve other species So, we have to include their activity also in this calculation if this reaction is a complicated one. So, we will have to introduce those part as well. Now, the activity of the species is expressed as a function of the nature of the species under consideration. So, it is basically a dimensionless value. So, in case of a compound with a gaseous mixture, the activity you can relate with this dimensionless constant gamma I and the partial pressure of that particular gas, and P0 is the standard pressure which is taken as 1 atmosphere, and the quantity that F, that is equal to this gamma I and this partial pressure of this gaseous product, that is called fugacity. So, in case of an ideal solution or liquid solution, the activity of the compound that belongs to the solution is expressed as this relation AI is Xi, where this is the mole fraction of the compound. So, the activity of pure monophasic compound that is equal to 1, because the fraction is equal to 1. So, activity of the solvent in a dilute solution can be taken as unit. In a solution where the compound is not in a single phase, then the term gamma will have to be included, and this lies in between 0 to 1. So, for a dissolved species in very low concentration, the activity is gamma I, where gamma is tends to 1. So, almost it is 1. So, it is basically concentration of that species with respect to C0, which is 1 mole per liter, and accordingly you can just exchange the activity with the concentration for a very dilute solution. So, next I will talk about the Faraday law, that the capacity, as I told, is the amount of the charge that is available in a charged cell. So, usually if you see a battery, it is printed on the cell as ampere hour, or sometimes for smaller battery as milliampere hour. So, 1 ampere hour is 1000 milliampere hour, and then you transfer into the second. So, it is 3600 ampere second. So, this is nothing but 3600 coulomb. So, discharge is usually done in a constant load current, and capacity can be defined as the integration of the current involved in this reaction from 0 to T. And from the electrochemical point of view, this is also equal to the number of moles of electron exchange and Avogadro number and electronic charge. So, this Na and E is defined as the Faraday constant. So, N is the number of moles of electron that is exchanged, and F is the Faraday constant. So, if you multiply the electronic charge with the Avogadro number, then you get this Faraday constant as 96485 coulomb per mole, and which can be transferred from the earlier relation. It can be transferred as 26.8 ampere hour per mole. So, the Faraday law basically that indicates the amount of electricity that is needed to change 1 mole of material, and that is equal to 96485 coulomb. So, the expression is the mass of the product that is formed, and that is related with the Faraday efficiency, which is usually taken as 1. M is the molar or molecular mass in gram per mole. Q is the charge that is usually taken in coulomb, and N is the number of moles of electron exchanged, and F is the Faraday constant, the value is 96485. So, this relation is actually estimated from the Faraday law, and that is basically the amount of electricity that is needed to change 1 mole of material, and that is equal to 96485 coulomb. So, now I will come back to lithium rechargeable battery, which already I had introduced in part of my earlier lectures. So, the construction is you have a current collector and cathode, usually aluminum is a current collector, and let us take the example of lithium cobalt oxide. And actually acetylene black is added, is a electron conductor inside the composite electrode, and PVDF binder is also mixed, so that it is properly adhered to the current collector. Usually a lithium based salt in a solvent, ethylene carbonate or diethylene carbonate, it is 1:1 mixture, it is taken as electrolyte, and anode is copper foil that is coated with graphite. So, that actually constitute the first prototype and also commercialized lithium ion battery. So, the advantage of lithium primary cell, which already I defined, that is extended to the secondary cell, and high power is available, and the lightness make them ideal for portable device, and Sony commercialized it in 1991. And electrolyte as with lithium primary cell, that is usually a non-aqueous solution of lithium salt in polar organic liquid. So, the mechanism, although I will come back to the mechanism later, but here the nominal composition of lithium graphite intercalation material is in graphite is intercalated, the lithium goes inside the graphitic layer, here the inside that lithium is intercalated, and the stacking sequence of hexagonal carbon layer converts from staggered to a ordered upon lithium intercalation. So, that takes place, and cathode is actually lithium cobalt oxide, and that is also an intercalation compound, so having a layer structure, and hexagonal packing is transformed into the cubic type upon discharge. Already while I was talking about the crystal structure, so I introduced this concept. Usually you can take about 0.5 moles of lithium from this structure. If you take more lithium out of the structure collapses. So, the anode reaction you can take that lithium is getting oxidized coming into the electrolyte, and cathode reaction is this lithium is basically intercalated into the partially delithiated lithium cobalt oxide. The cell reaction is this one coming from this anode and cathodic reaction. So, you can have a simplified reaction as well. So, where lithium is basically oxidized at lithium plus, and in cathode reaction this cobalt ion, which was in +3 +4 valence state, that is reduced to +3 valence state. So, that is the simplified full cell reaction, which is occurring during the discharge of the battery, where electron is being fed to the load to do the work. So, I can apply the Faraday law. So, theoretical gravimetric capacity, that is the total charge per mass, and that is N into F by molecular weight. So, we can transform the coulomb into ampere hour, the way I introduced earlier, and grams into kilograms or amperes into milliamperes. So, the gravimetric capacity we can get as 1000 into Nf and 3600 into capital M. So, the capacity in this unit milliampere hour per gram is 1000 into N into Faraday constant divided by 3600 into capital M. So, if you just simplify it, you will get this simple relation 26801 number of electrons that is involved in this reaction by molecular weight. So, if you take cathode, instead of lithium cobalt oxide, I have taken an example of lithium manganese oxide. So, lithium manganese oxide this reaction takes place while discharge. So, here I have taken x equal to 1 for complete extraction, not like lithium cobalt oxide where only 0.5 moles you can take out. and the relation is basically Mn2O4, lithium is intercalating there, and it is taking electron which is coming from the anode part, and basically it forms back LiMn2O4. So, again I apply the Faraday law, 26801 number of electron by m. So, here you can see that this part number of electron is here 1, and this value, this molecular weight of lithium manganese oxide, I can estimate this is for lithium, this is for manganese, and this is for oxygen, and I get the capacity about 148 milliampere hour per gram. Similarly, for graphitic reaction also I can do the same thing and calculate from the Faraday law. This capacity is 1 full electron is exchanged, and this is for the carbon molecular weight, and multiply this term 26801, and it gives me 372 milliampere hour per gram. So, the full cell capacity, these two individual capacitor as if they are connected in series. So, from the normal series capacitance law, I can get the capacity of the full cell as 1 by 372 and 1 by 148 milliampere hour per gram. So, it is coming about 106 milliampere hour per gram. So, there is no cathode material till date which can match the capacity of the graphite anode. So, you can see the graphite anode is 372, and the for cathode the capacity, the half cell capacity is 148 milliampere hour per gram. So, once you have a full cell constructed, the actual capacity is less than the individual capacity. So, I am leaving it to you to explain the implication of this fact. Okay. So, that we will discuss in a part of an assignment problem later. So, the reference for this particular lecture is the book by Glaze and Gaines, Lithium Batteries, and that you can use chapter 2 as study material, and this is an excellent book by John Newnham. This also can be used several chapters 1, 2 and chapter 8 in particular, which will clarify the basic idea. So, let me conclude this lecture. So, first I illustrated the redox potential of one single electrode, the concept of redox potential. Then we talked about electromotive force of a particular electrochemical cell. Then derived Nernst law, which will allow you to estimate the voltage under non-standard condition, and subsequently we also talked about Faraday law, illustrated the Faraday law, and finally we use Faraday law to estimate the discharge capacity of a typical lithium ion full cell, taking graphite as the so called negative electrode and lithium manganese oxide spinel that as positive electrode. Thank you for your attention.